Okay, let me start with the questions. How many of you have an IoT device at home? Okay, very few. I can see that we are in a security and privacy conference. At the moment, currently, there are 22 billion Internet of Things devices in use. Some devices listen to us, some watch us. Others know what we watch. Some of them send our traffic across the internet, sometimes unencrypted, leaving the user vulnerable. Some are very vulnerable to malware attacks, for example. Nowadays, you can go to a shop or online and buy these IoT protection systems. We call them IoT safeguards. And they claim to give back control to the user. They do the device detections, intelligence profiles, they implement security, they claim to do vulnerability assessment, brute force protection, anomaly detection. They provide privacy, content filtering, network intrusion prevention systems. It's great, right? If only they were working. In this study, we demonstrate that these safeguards may currently be ineffective for some security and privacy risk. Their cloud interactions and also data collection methodology also introduce additional privacy risk. So in this work, we want to know what are the privacy and security implications, how safeguards work. If the safeguards actually detect the threats that they claim to detect, and what are the side effects of the safeguards? This is challenging because it's very difficult to automate the auditing for such a closed systems. So we need a black box approach. We cannot actually go there, and the code is not open source. And it's very difficult actually to perform IoT experiments nowadays because there is a lack of automation and emulation tools, and there is a lack of standard testbed. So our contribution is a large IoT testbed enable us to experiment with real-world scenarios for commercial IoT safeguards. When selecting the safeguards, I'm based in Europe, so we consider the ones that are commercially available there, and we categorize them in 4 different kinds. So we have software safeguards that are basically add-ons that you can add to your smart router. Usually they partner together with some commercial router, like, for example, D-Link or Asus. You have router safeguards that are boxes that you can buy, connect to your router, and they act as your router. So all the content from your IoT devices is actually go there. Then you have bridge safeguards. They are between the inter-service provider and your router, and they do the packet inspection. And then you have R-spoofing safeguards that have actually only one interface that you connect to your router, and then they use R-spoofing for making the IoT devices believing that they are the router. For experimenting with these devices, we built an advanced IoT testbeds. We bought hundreds of IoT devices. And we have a gateway that actually acts as the controller and is in the interface with the inter-service provider. We have the safeguards. We have an IoT bridge for actually experimenting with the IoT devices, and it's connecting the IoT devices to the safeguards. These safeguards usually can be controlled through a smartphone app. So we have an Android phone for getting all the notifications from the safeguards, and we perform packet captures in the gateway and the IoT bridge. The gateway and the IoT bridge are also able to emulate security and privacy threats from the IoT devices. When we consider the first research questions, we want to know if these devices are actually using the cloud to operate or if they operate locally. And we also wanted to understand if they use third-party services to operate. For doing so, we basically capture all the traffic from the safeguards, and we consider the destinations that were contacted. And we categorize the destinations in first-party or non-first-party. For understanding locality, we took the traffic from the IoT devices and we compared with the traffic to some destinations of the safeguards and see if actually the trends of the traffic, of the pattern, was used. First results are really concerning. So all the IoT safeguards use the cloud to operate except one, Firewall. And they're also using third-party services, like, for example, Avira is contacting mixpanel.com, that is a tracker services. We also have McAfee using, for example, appmeasurements.com, that is a Google services. Thingbox is using third-party services for operating speed tests, like, for example, MLab or snapcraft.io. And the destinations contacted are non-first party. There is a feature that safeguards actually offer to the user, that is IoT devices identifications. So every time you are connecting a new IoT devices in your home, the safeguards recognize automatically, claim to recognize automatically the devices. Actually, we discovered that only few of them, only 3, do this correctly, and just for some of the IoT devices we had in our testbed. And this is concerning because sometimes safeguards offer services that are specific to one vendor. Like, for example, in this case, we have the services of muting all the smart speakers in your home. And if the IoT devices is not correctly identified, how is it possible to correctly actually use these policies? For the second research questions, we want to know if actually the safeguards are detecting the threats that they're claiming to detect. Usually when a threat is detected from the safeguards, they send a notification to your smartphone. So we just list some common IoT threats, security and privacy threats, like, for example, anomalous behavior, weak passwords, DOS attacks, simply like starting connection to malicious destinations. And we also emulate some privacy threats, like, for example, personal identifier information exposure, unencrypted traffic, DNS over HTTPS. And we did this experiment 30 times. And if only once the threat was detected from the safeguards, then we say that the threat is detected. These are the results. So most of the safeguards do not actually detect the threats that they claim to detect. Only 3 out of 14 threats are detected by some of them, and sometimes it takes between 30 seconds and 3 minutes for detecting a DOS attacks, for example, like HTTP flooding. And we repeat these experiments many times in 6 months, and we saw that actually there is time consistency. So the safeguards do not improve over time. For the third research questions, we want to understand if these safeguards implement traffic overhead, if they overprotect, and what are the privacy implications, reading the privacy policies. For the first sub-questions, we connect 12 IoT devices to the safeguards for 1 month, and then we just check the notification to see if they were notifying something, and we did nothing, so we were just checking if they were notifying something that didn't happen. For the second, for the network traffic overhead, we just captured the traffic from the IoT devices and in the gateway, and then we subtract the traffic of the IoT devices for understanding the overhead of the safeguards. And then we manually inspect privacy policies for understanding what are the policies in these cases. Most safeguards do not overprotect. So in 1 month, we got only 1 notification that was from Bitdefender, in which they basically told us that one destination was malicious destination was contacted, but this wasn't the case. We manually inspected packet captures, and we said that this was like okay destinations to contact. Some of the safeguards introduce significant traffic overhead, until, well, at least 10% of the traffic overhead, until 60% in the case of Thingbox, they use R spoofing for operating. Privacy policies are also concerns. So most user information is shared with third-party entities, sometimes without any anonymizations, and most of our data are shared outside our privacy jurisdictions. So we saw that the majority of the traffic is sent to the cloud. So these safeguards use the cloud to operate. In reality, what we will need in the future is solution at the edge. We will need a smart router that is able to perform all this processing of understanding threats directly in our home. And this is something we are currently exploring. This is future work of us. So in conclusion, we did a quantitative approach for auditing IoT safeguards, analyzing the data collection and sharing practices. We implement a scalable methodology for evaluating the effectiveness of the safeguards against non-IoT and network threats. And we saw that often the safeguards do not provide the protection they claim to do. And also their data sharing practices may introduce potential privacy threats to the users. We contacted the vendors of the safeguards, and we are actually working with some of them. Like we're working with Thing for understanding energy consumption for IoT devices. I'm meeting actually the director of IoT of Bitdefender tomorrow here in San Francisco. And all the data and the software that we use for this work are actually currently available there. I hope you do a good use of it. Thanks for your attention. I'm happy to take any questions.
Do we have any question? Okay. If not, I can ask one question. So whenever like you are analyzing those like privacy policy and other stuffs, like are you also considering like the existing regulations like GDPR and this type of like stuffs there?
Yeah, so we didn't do this part automatically because it was very few safeguards, so we could do this manually. And because we were based in UK, we considered GDPR.
Whenever like you are saying like some of the like the you're also categorizing some like destinations, a number of destinations, right? So are you like thinking that like they go to like other location than the original manufacturer website, or like how do you like define those destinations?
So basically we use WHOIS for understanding the country of origin, and then we use another tool that is called Passport for getting geolocations. And then we checked that actually the server was the same as stated in the privacy policy. The location of the server was the one stated in the privacy policies.
Great, thank you. So
you're welcome.
If we don't have any questions, so let's thank the speaker again.
Thank you. Thank you.